Probably the strength criterion that is most widely used for ductile materials such as metals is that proposed independently at different times and using slightly different approaches by several scientists: the Polish engineer Titus Maximilian Huber, the German engineer Heinrich Henke, and the Austrian mathematician Richard von Mises. Nowadays, it's mostly known as von Mises criterion. The critical index underlying this criterion is the distortion strain energy density, where density means per unit volume. The distortion strain energy density is the part of the strain energy density responsible for the change in shape of an elementary volume. This is why von Mises' theory of failure is also called maximum distortion energy theory. How can we compute the distortion strain energy density? First of all, recall that the strain energy density or elastic potential, omega, of any linear elastic material can be expressed as 1/2 of sigma ij epsilon ij, where a double summation over the subscripts I and j, which range from 1 to 3, is implied. We know that the stress tensor can be decomposed into an isotropic or hydrostatic stress and a deviatoric stress. Namely, any stress component sigma ij can be expressed as P delta ij plus Sij, where delta ij is the so-called Kronecker delta, which is 1 if I is equal to j and 0 otherwise. P is called isotropic pressure and is 1/3 of the trace of the stress tensor sigma 11 plus sigma 22 plus sigma 33. Synthetically, P is 1/3 of sigma ij delta ij. Sij are the components of the deviatoric stress tensor. The deviatoric stress indicates how much the total stress sigma differs or deviates from the hydrostatic stress P delta ij. We can perform a similar decomposition with the strain tensor, and we can write epsilon ij equal to E delta ij plus eta ij. Here E is 1/3 of the trace of the strain tensor epsilon 11 plus epsilon 22 plus epsilon 33. Synthetically, E is equal to 1/3 of epsilon ij delta ij and corresponds to 1/3 of the volumetric strain. Thus, the term E delta ij accounts for the change in volume of a material element. Eta ij is called a deviatoric strain and accounts for the change in shape of a material element. Using these decompositions, the strain energy density omega can be rewritten as 1/2 of P delta ij plus Sij times E delta ij plus eta ij. But as the deviatoric tensors are traceless, we'll simply get omega equal to 1/2 of 3 times Pe plus Sij eta ij, as delta ij is 1 plus 1 plus 1, that is 3. The first term, omega v, equals to 3/2 of P times E, and is the volumetric energy density, which is responsible for the volumetric strain of a material element. By difference, the second term, omega d equal to 1/2 of Sij eta ij, is the part of the strain energy density responsible for the shape variation of the element, and is called distortion strain energy density. As yielding in metals is found to be independent of the hydrostatic pressure, only omega d has to be bounded to avoid yielding. Thus, von Mises' criterion states that omega d must be less than or equal to omega d0, where omega d0 is the allowable distortion strain energy density for a given material. Let's rewrite this condition in terms of stresses. First of all, recall that each deviatoric stress is related to the corresponding deviatoric strain by a formula that is formally equal to that used to relate shear stresses and shear strains, That is, Sij is equal to twice g times eta ij, where g is the shear modulus of the material. The distortion strain energy density omega d can thus be rewritten as Sij divided by 4g. But we want to get a condition in terms of total stresses rather than deviatoric stresses. So let's use the definition of deviatoric stress. Sij is equal to sigma ij minus p delta ij. And let's replace this expression in that of omega d. So we get omega d equal to sigma ij minus p delta ij times sigma ij minus p delta ij divided by 4g. Again, delta ij is 3. Sigma ij delta ij is the trace of the stress tensor, that is 3p. So if we expand the product in the expression of omega d, we get omega d equal to sigma ij minus 3 times p squared divided by 4g. How do we get the allowable value of the distortion strain energy density omega d0? The simplest way is to get it from a uniaxial tension test. Assume that all the stress components vanish but one, say sigma 1,1, and let's denote it simply by sigma. In this case, the distortion strain energy density omega d is sigma squared minus 3 times 1/3 of sigma squared divided by 4g. That is sigma squared divided by 6g. If sigma 0 is the yield stress, or more generally the allowable stress, the allowable distortion strain energy density omega d0 is sigma 0 squared divided by 6g. So we can rewrite von Mises criterion in terms of total stresses as sigma ij minus 3 times p squared less than or equal to 2/3 of sigma 0 squared. Note that g cancels as the shear modulus is always strictly positive. If we expand this expression, we can write von Mises criterion in terms of Cartesian stresses as sigma x squared plus sigma y squared plus sigma z squared minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x plus 3 times tau xy squared plus 3 times tau yz squared plus 3 times tau zx squared less than or equal to sigma 0 squared. Eurocode 3 uses this formula in plane stress conditions, that is with sigma y, tau xy and tau yz equal to 0 for the verifications of the resistance of steel cross sections. It can be useful to express this criterion in terms of principal stresses. To do this, simply set all the shear stresses equal to 0 and replace normal stresses by principal stresses. The criterion now states that 1/2 of sigma y minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared must be less than or equal to sigma 0 squared. In the space of the principal stresses, this inequality defines an infinite circular cylinder with axes coinciding with the hydrostatic axis, sigma 1 equal to sigma 2 equal to sigma 3. This means that a material obeying von Mises criterion can withstand any isotropic stress similarly to materials obeying Tresca criterion. If one of the principal stresses is 0, for instance, if sigma 3 is 0, von Mises criterion in plane stress conditions reads sigma 1 squared plus sigma 2 squared minus sigma 1 sigma 2 less than or equal to sigma 0 squared. This inequality defines an elliptical domain in the plane sigma 1 sigma 2 with principal diameters rotated of plus or minus 45 degrees with respect to the Cartesian axis. If we compare the domains of the allowable stresses according to von Mises criterion and to Tresca criterion for the same value of the admissible or yield stress sigma 0, we can see that von Mises is less conservative than Tresca, as Tresca domain is entirely inscribed within von Mises domain. Which one is more appropriate for metals? Well, if we compare the boundaries of von Mises and Tresca domains with the results of yield tests on steel specimens subject to biaxial tension, owing to the experimental scatter, we can see that both strength criteria fit the experimental points. Thus, both criteria are equally reliable for metals. But usually von Mises is preferred over Tresca as yield condition in most numerical applications, basically for its ease in being implemented in computer programs, as it is defined by a single expression rather than by 6. Finally, consider a beam-like stress, that is a particular plane stress in which only a normal stress sigma and a shear stress tau are non-zero. The general expression of von Mises criterion in terms of Cartesian stresses simplifies to sigma squared plus 3 times tau squared less than or equal to sigma 0 squared. This inequality defines an ellipse in Morse plane, which is a little more chubby than Tresca ellipse. Again, this is because von Mises criterion is less conservative than Tresca criterion for a given admissible stress sigma 0. We can rewrite this inequality in the form sigma Vm less than or equal to sigma 0, where sigma Vm is called von Mises equivalent stress, and is given by the square root of sigma squared plus 3 times tau squared. The definition of equivalent stress is similar to that obtained from Tresca criterion. It is sufficient to replace a 4 by a 3. To conclude this subject, it is worth to mention that von Mises criterion has also different physical interpretations. Maybe the most common interpretation is that von Mises criterion is actually a limitation of the second invariant of the deviatoric stress J'2, which is given by 1/2 of Sij Sij. Apparently, J'2 is proportional to the distortion strain energy density and must not exceed 1/3 of sigma 0 squared. Another interpretation is that given by the Russian mathematician Novozhilov, who noticed that the distortion strain energy density is proportional to the average shear stress tau AB, acting over an infinitesimal sphere centered at a point of the body. And indeed, it's possible to show that tau AB squared is equal to 1/15 of sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared, and must not exceed the square root of 2/15 times sigma 0. Finally, von Mises criterion can also be interpreted as a limitation of the so-called octahedral shear stress tau oct. The octahedral stresses are the normal and the shear stress acting on an infinitesimal surface that makes equal angles with the principal stress directions. Without going into too many details, it is possible to show that in particular tau oct is nothing but the square root of 2/3 times J'2. And accordingly, the criterion can also be expressed as tau oct less than or equal to 1/3 of the square root of 2 times sigma 0.